Welcome to the Module 6 outline. Energy is the ability to do work. Kinetic energy is the energy due to motion. And potential energy is the stored energy in matter due to its position or composition. What are some different units associated with energy? The metric unit for energy is the joule, which is given the abbreviation of a capital J. The English unit for energy is the calorie, which is given the abbreviation lowercase cal. But the calorie that's labeled on food is actually a kilocalorie, which is given the symbol kcal. And that is often referred to as a food calorie, and sometimes they will write it as a capital CAL to indicate that it is a food calorie. To convert between the two units, 1 calorie is defined as 4.18 joules. Temperature is a measure of the average kinetic energy of particles in a system. As the kinetic energy increases, which I'll indicate as Ke, the temperature is also going to increase, which I indicated as a T. In order to convert from Fahrenheit to Celsius and vice versa, there are two equations that we could use. They are essentially the same equation, just rearranged. In the first equation, we could have Fahrenheit, which is given the symbol capital F, is equal to 9/5 times the Celsius, which is given the symbol capital C, plus 32. If we do some algebraic rearrangements, we could get that the Celsius temperature is equal to 5/9 times the Fahrenheit temperature minus 32, with the Fahrenheit minus 32 being in parentheses. To convert between the Kelvin and Celsius temperature, we use the equation that Kelvin, given by the symbol capital K, is equal to the Celsius temperature plus 273.15. Let's convert 1350 degrees Fahrenheit to Celsius. We know that Fahrenheit is going to be equal to 9/5 Celsius plus 32. And the Fahrenheit temperature is 1350 degrees Celsius. If I plug that into the equation, I just need to solve for the Celsius temperature. I would want to subtract 32 from both sides. I would get 1318 as my new value. That's equal to 9/5 Celsius. To isolate the Celsius temperature, I would multiply both sides by the reciprocal of 5/9. That would cancel out the numerical values on the right, and 5/9 times 1318 gives me a value of 732 degrees Celsius. I am going to keep 3 significant figures for the sake of this problem. Convert 695 degrees Fahrenheit to Kelvin. Now we want to go one step further than just converting to Celsius, so we'll use both equations. Again, the Fahrenheit temperature is equal to 9/5 Celsius plus 32. The Fahrenheit temperature is 695. If I subtract 32 from both sides, I get a value of 663. That's going to equal 9/5 Celsius. If I do the same process as in the previous slide by multiplying by 5/9, I would get that the Celsius temperature is going to be 368.33 degrees Celsius. I don't want to stop there though. I want to find out the Kelvin temperature. So the Kelvin temperature is Celsius plus 273.15. We found that the Celsius temperature was 368.33 degrees. If I add 273.15 to that, I get that the Kelvin temperature is going to be 641 Kelvin. And again, I'm going to follow the idea that 695 at the initial value had 3 significant figures, and so it probably makes sense to report my final answer with 3 significant figures. Heat is the transfer of energy between the system and its surroundings. A warmer object will transfer its kinetic energy to a colder object and not vice versa. An exothermic process is a process in which heat is lost by the system to the surroundings. If you are the surroundings, an exothermic process would feel warm to you. An endothermic process is a process in which heat is gained by the system from the surroundings. If you are the surroundings, an endothermic process would feel cold to you. What are systems and surroundings? The system is a particular part of the universe that we have decided to study. It can be essentially anything that we would like to designate as a system. The surroundings would then be everything that is outside of that system. There are 3 different categories of systems. The first type of system is called an open system. In an open system, both mass and energy can be transferred between the system and the surroundings. What would be a good example of an open system? A human being would be a good example. We can transfer mass in and out of a human being, and heat and energy can be transferred in and out of our body. In a closed system, energy can be transferred between the system and the surroundings, but mass cannot be transferred. What would an example of a closed system be? An unopened can of vegetables would be a good example. The heat and energy could enter into the can and could leave the can, but nothing in the can is actually going to leave in terms of the mass. In an isolated system, neither energy nor mass can be transferred between the system and the surroundings. What is an example of an isolated system? Isolated systems, if we truly look at the definition, there's really one isolated system, which would be the universe, because I'm not sure exactly what's outside of that system, so neither energy nor mass can be transferred from this universe unless there are more universes. Sometimes we treat other systems as being like isolated systems, just so that it makes certain concepts easier for us to grasp initially. There are 2 different kinds of functions. There is what's called a state function and a path function. A state function is a function or some measurement that depends only upon the initial and final state and not the specific pathway taken. A good example of a state function is a temperature change. If I tell you that the temperature has changed 15 degrees, we don't know what path it's taken to get that 15-degree change. We just know that it's changed 15 degrees. One way that we can identify that a function is a state function is that these kinds of things will be written with a capital letter. That's why in equations we write temperature with a capital T. A path function, on the other hand, is a function that is going to depend on the specific pathway taken. What is an example of a path function? Work is going to be an example of a path function. How much work you do is going to depend on the path that you take. How much heat is given off will also depend on the path that you take. The internal energy, which is given a number of different symbols depending on the material given. In this case, I'm going to use the capital U as internal energy. It's the sum of all the kinetic and potential energies of particles in a system. The law of conservation of energy states that energy can neither be created nor destroyed. Rather, the energy can only be transformed from one form to another form. The first law of thermodynamics is essentially a restatement of the law of conservation of energy. It states that heat and/or work gained by the system is going to be lost by the surroundings, so that the total energy of the universe is conserved. We could indicate that as saying the change, given by that symbol that looks like a triangle, so the change in internal energy of the universe is going to be equal to 0. Since energy can't be created or destroyed, it can be said that the change in the internal energy of the system, so if the system changes its energy, and then the change in the internal energy of the surroundings, if those are both added up, they should equal 0. If the system is losing energy, then the surroundings should be gaining energy and vice versa. We can also say that energy is the capacity to do work or to transfer heat. There's essentially two processes that could occur for energy. The energy could be used to do work, or some of that energy is going to be transferred into heat energy. And what we can state is that the change in the internal energy is going to be equal to the heat, which is given that symbol Q, plus the work, which is given the symbol lowercase w. Both the heat and the work are path functions. They don't depend on the path. They do depend on the path that's taken, whereas the internal energy is a state function, which doesn't depend on the path that you take. So it's an interesting combination of equations there. When we are calculating work and heat in the internal energy equation that you saw on the previous slide, there are signs, positive or negative, that are associated with the heat, Q, work, W, and the change in the internal energy, delta U. If the process is where heat is absorbed by the system, which is an endothermic process, the sign on the heat will be a positive sign. When the heat is released by the system, it's exothermic, then it will be a negative value. For work, when work is done on the system, so a volume decrease, such as me pushing a balloon so that it got smaller, I would be adding energy to the balloon, and so that would be a positive value for work. Whereas if work is done by the system, a volume increase, let's say that the balloon got bigger without me doing anything, that would be a negative value, which means that something inside of that balloon is releasing energy in the form of work. We can combine both of those together and say that the internal energy, if that's absorbed overall by the system, that would be a positive value. And if internal energy is released by the system, it would be a negative value. Let's calculate the change in the total internal energy for a system that releases 1.34 times 10 to the 4th kilojoules of heat and does 2.98 times 10 to the 4th kilojoules of work on the surroundings by the system. The equation that we're going to use is that the internal energy, delta U, is equal to the heat Q plus the work W. But before we just go and plug in any numbers, what we need to decide are the signs on the heat and on the work. For example, it says that it releases 1.34 times 10 to the 4th kilojoules of heat. And so anytime that heat is released, that is going to be a negative value. For the work, it says that the system does 2.98 times 10 to the 4th kilojoules of work on the surroundings by the system. And so when work is done by the system, that is also a negative value for work. So it would be negative 2.98 times 10 to the 4th kilojoules. So now that we've decided that both of those are negative values, then we can add both of those values up. And when we do that, we will get that the change in the internal energy is going to be a negative 4.32 times 10 to the fourth kilojoules, which indicates that internal energy was released. The specific heat capacity, which is designated by the symbol lowercase s, and in some other textbooks is indicated by the lowercase c. It is the amount of heat that is required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Because of that definition, the units on a specific heat are joules per gram degree Celsius. When we want to determine the amount of energy or heat that is required to heat a certain material, and we also know the mass of the object, then we can use the equation that heat, given the symbol Q, is equal to the mass, given the lowercase m, multiplied by the specific heat, which we gave the symbol lowercase s, multiplied by the change in temperature, which we give the symbol delta T, that will give us the heat. And so we could then simplify that down and say Q equals ms delta T, where delta T, the change in temperature, is really the final temperature minus the initial temperature. We want to heat 100 grams of water from 25 degrees Celsius to 45 degrees Celsius. How much heat will be required? I'm indicating here that the specific heat of water is 4.18 joules per gram degree Celsius. In this case, the equation that we're going to use is Q equals ms delta T. If it helps, write out the words instead of the letters, because sometimes the difficulty is identifying what the letters mean in relation to the words. So we're trying to find the heat, which is Q. So I'm going to leave that blank and say Q equals the mass. Let's identify and see that the mass is 100 grams. That's M. So 100 grams. S is the specific heat. And then for water, it's 4.18 joules per gram degree Celsius. And delta T is the change in temperature. So the change in temperature is going to be the final temperature of 45 degrees Celsius minus the initial temperature of 25 degrees Celsius. That would give us a value of 20 degrees Celsius as the temperature change. I would then multiply those three values together, and I would get 8,360. The unit on that, grams, are going to cancel out. The degrees Celsius will also cancel out, and I'll be left with a unit of joules. You have 595 grams of gold metal at 23.4 degrees Celsius. You add 4.5 kilojoules of heat to the piece of the metal. What is the final temperature of the gold? Again, the equation that we're going to use is Q equals ms delta T. Let's rearrange this one and find out that we're going to solve for the final temperature, which is inside of the delta T. So I'm going to divide by ms. I'll get that Q divided by ms is going to equal the change in temperature, which I will also write as T final minus T initial. So let's plug in and find out that Q is the heat, which it says 4.5 kilojoules. It might not be noticeable. Let me find out the specific heat for gold. If I look at a chart, which is in your periodic table or your course pack, the specific heat of gold is 0.127 joule per gram degree Celsius. I wanted to look at that to point out that the specific heat has units of joules, so we need to convert the 4.5 kilojoules to joules first. If we do that, we get that the heat is 4,500 joules. So I have 4,500 joules divided by the mass, which is 595 grams. That's going to be multiplied by the specific heat that we looked up in is 0.127 joule per gram degree Celsius. And that's going to be equal to the final temperature, which is what we're looking for, minus 23.4 degrees Celsius for the initial temperature. When I enter in the values on the left, the 4500, the 595, and the 0.127, I get an answer of 59.55. That's going to be equal to the final temperature minus 23.4. We should pay attention that one of these values, the 4500, only has 2 sig figs. So my measurement that I have here probably only has 2 sig figs also. I'm not going to round it off right now. I will add 23.4 to both sides, and what I'll get is that the final temperature is equal to 82.95. We're adding and subtracting. As I mentioned, the 59 probably only has 2 sig figs, and so addition and subtraction would say, well, there's not going to be any decimal places after that, so I should probably chop off the decimals on this whole problem and get that the final temperature is going to be 83 degrees Celsius. If I wanted more precision, I would need to measure some of these differently. Heat capacity, which is given the symbol capital C without a degree sign so that it's different from degrees Celsius. The heat capacity is the amount of heat that's required to change the temperature of an object by 1 degree Celsius. This is a bit different than the specific heat capacity because the specific heat capacity is specific to a certain type of material, whereas the heat capacity can be measured for a whole object that is maybe made up of a bunch of different things. And the difference between the two is the units. In the specific heat, the units include a gram value, whereas you're going to notice here that the units on a heat capacity are just joules per degree Celsius. When we want to determine the amount of energy or heat that's required to heat a certain material, and in this case we don't know the mass of the object because it's not important, then what we use is we use the equation involving the heat capacity, which says that the heat with the symbol Q is equal to the heat capacity given the symbol capital C multiplied by the change in temperature, which is given the symbol delta T. And again, delta T is T final minus T initial. The heat capacity of a calorimeter, a device that's used to measure heat change, is 450 joules per degree Celsius. If the temperature of the calorimeter increases from 31 degrees Celsius to 35.9 degrees Celsius, how much heat in joules was added to the calorimeter? If we take the Q, the heat is going to be equal to this heat capacity, capital C, multiplied by the change in temperature, what we'll find is that the heat capacity of the calorimeter is 450 joule per degree Celsius, and we would want to multiply it by the change in temperature. In this case, the change in temperature is 35.9 degrees as the final temperature and 31 degrees as the initial temperature. That's a change of 4.9 degrees Celsius. So I'm going to multiply the heat capacity by 4.9 degrees Celsius. The calculator is going to show me an answer of 2,205 joules, but for this problem I should only have 2 significant figures, so I'd really want to just keep the first 2 and then have the others as zeros since I'm not rounding anything up. And so I would say that the heat absorbed by the calorimeter is 2,200 joules. Calorimetry is a technique for determining how much heat is released or absorbed in a process or a reaction. A 5.80 gram serving of Yummy in Your Tummy grape nuts is burned in a bomb calorimeter with a heat capacity of 43.7 kilojoules per degree Celsius. During the combustion, the temperature of the calorimeter increased by 1.92 degrees Celsius. Calculate the energy content in kilojoules per gram of grape nuts. So we want to know the kilojoules per gram of energy in there, and it helps to keep that in mind as we go along. It's kilojoules per gram of grape nuts. We know that there are 5.8 grams of grape nuts. I'm going to write that as the denominator of this process. What we really want to find is kilojoules of heat released or absorbed, in this case released because the temperature increased. And so what we would do is we would take the heat capacity is 43.7 kilojoules per degree Celsius. It says the temperature increased by 1.92 degrees Celsius. And so we would say Q equals capital C heat capacity times delta T change in temperature. The heat capacity is 43.7 kilojoule per degree Celsius. The change in temperature is 1.92 degrees Celsius. Those calculations give a heat value of 83.9 kilojoules overall. And so I would then want to write down that there's 83.9 kilojoules divided by 5.8 grams. We didn't use the 5.8 grams in the calculation itself because those are referring to two different things. And notice there also isn't any gram in our unit, so that would have created some gram unit confusion. That value would be, those two values would be, if I divide 83.9 by 5.8, that would give me a value of 14.5 kilojoules per gram. You might have noticed that I wrote a negative. That's to indicate that this reaction is releasing heat. Hence why there was a temperature increase, and because of that, you would write this value as a negative value to indicate that heat is being released. A 406 gram piece of metal at 100 degrees Celsius is dropped into a cup containing 100 grams of water at 25 degrees Celsius. The final equilibrium temperature of the copper and the water together is 45.4 degrees Celsius. What is the specific heat of the metal? In this case, what we are going to use is the law of conservation of energy, which states that the energy that one thing is absorbing is the same as what something else is releasing, because we're combining two things that are at different temperatures into the same container. They're both going to end up at the same final temperature. So what we want to do is what we can say is that the heat that the metal is going to be losing is equal to the heat that the water is going to be absorbing. And so it may help to solve this in two separate steps and also write down what information we know. For the metal, let's write down the metal on the left. We know that it's a 406 gram piece of metal, so that's the mass. We don't know the specific heat of that metal, so that's what we're trying to find. We know that it is starting, its initial temperature is 100 Celsius, and its final temperature is 45.4 Celsius. If I wanted to calculate the change in temperature, the final temperature would be 45.4, and the initial would be 100. And so that would give us a value for the change in temperature of negative, I don't exactly know off the top of my head. Let me calculate that really quickly. 45.4 minus 100. It's going to be negative 54.6 degrees Celsius. For the water, we know there's 100 grams of water. We know that the specific heat of water, it is water, and we can find that on the chart of specific heats in the course pack. Water is 4.18 joule per gram degrees Celsius. we can also find that the change in temperature of the water is going to be 45.4 degrees Celsius minus 25 degrees Celsius. That one's a little bit easier for me to calculate. That would be 20.4 degrees Celsius. I'm showing both of those values so that we can decide we know more about the water. There are other ways that we could show this too, but I'm going to show how much heat the water has absorbed because I know the three values required. In this case, I am given masses, so it's going to be mass times specific heat times change in temperature. Those are all for the water. The mass of the water is 100 grams. The specific heat of the water is 4.18 joule per gram degree Celsius, and the change in temperature of the water is 24.4 degrees Celsius. Therefore, the heat that the water absorbs is going to be 8,527 joules of heat. I'm not going to worry about the significant figures at this point. But what we also know is that the heat that's absorbed by the water is going to be the heat that's released by the metal. There is one difference in this case. Since the heat is released by the metal, that would be a negative value since energy is released in that step. And so what we can then do is we can then say that the heat of the metal is going to be equal to the mass of the metal times the specific heat times the change in temperature of the metal. We're going to now report that the heat is 8,527 joules except negative. The mass of the metal is 406 grams. The specific heat is what we're trying to find, and the change in temperature is a negative 54.6 degrees Celsius. When we solve for the specific heat, we get that the specific heat of the metal is 0.372 joule per gram degree Celsius.